Okay. Hello, everyone. We are very happy to have Ashrujit here with us. He is a PhD from the University of Washington, where he finished in 2023. Since then, he has been a postdoc at Carnegie Mellon, and his work is somewhere in between theory and practice of cryptography. So this includes things like security analysis of common schemes like SHA-2 and SHA-3. It also includes algorithms towards making cryptography more practical. And I'm excited about this talk because my aunt has this habit of taking her name and Gmail as the password for Gmail and side that. So I wanted to know what your thoughts are on that. You can start.
Thanks. So hello, everyone. So today I'll give you a broad overview of my research. The central theme of my research has been bridging the theory and practice of cryptography. Feel free to interrupt me at any point to ask questions. So in recent times, cryptography has been deployed on a massive scale, and some examples include billions of end-to-end encrypted messages sent on popular apps like WhatsApp, or the large number of TLS connections being made per second on the internet. Cryptography is one of the success stories of theoretical computer science in the sense that it is an area that has seen large-scale deployments in practice. However, going from theory to deployments is not a very straightforward process, and it involves a pipeline. The first step in the pipeline consists of design of new theoretical constructions, and this is followed by a standardization process, usually undertaken by an organization like NIST, the National Institute of Standards and Technology. They send out a call for candidate constructions for a primitive. Then the submitted candidates, which are publicly available, are vetted for weaknesses, attacks, and flaws by the cryptography research community. This helps whittle down the number of candidates. And after several iterations, NIST finally chooses one or a few of the candidates to be standardized. One very important part of recommending standards is specifying the exact choice of parameters to use. The last step in this pipeline is engineers deploying these standards in large-scale cryptographic systems. However, in this pipeline, several different challenges crop up at various points, and my work has primarily focused on identifying and addressing these challenges by building new theory. The most challenging thing in the pipeline from theory to practice is the choice of security parameters for candidates that are standardized. The challenge stems from the fact that typical cryptographic theorems deal in asymptotic terms. For example, they show that assuming some problem is hard, a cryptographic scheme is secure for large enough choice of parameters. While that's a perfectly acceptable thing in theory, in practice, we need to actually set these parameters to concrete values. The exact value of a security parameter determines, in particular, how long it would take an adversary to break a cryptographic system. As an example, the graph here shows when the security parameter is set to 2048, it takes much longer to break security than when it is set to 1024. So a larger security parameter implies more security. On the other hand, a larger security parameter means it takes longer to evaluate a cryptographic primitive. The graph here shows an example of how much slower a cryptographic primitive becomes when we increase the security parameter from 1024 to 2048. The larger the security parameter is, the less efficient the cryptographic system. Therefore, there is an inherent tension between security and efficiency that underlies the choice of security parameter. My work contributes towards resolving this tension by proving exact guarantees about the best possible adversaries on practical cryptographic systems. So this allows us to set parameters in a way knowing that there cannot be any adversary that does better, and hence we can choose the smallest parameters that guarantee security. This, of course, makes cryptographic systems more efficient. In my research,
What do you mean when you say exact?
So it's like what you would say like a tight bound. Like, for example, you show that you prove like a quantitative bound showing that no adversary can do better than some amount, like given some amount of resources. no adversary can have like probability of breaking the cryptographic system in terms of some function of the resources, and then show a particular adversary that achieves that function. So like it's tight in some sense.
Yeah, but my question is it tied up to constants, up to polynomial factors? Is it really?
So we care about tied up to constant factors. Like it's fine if it's like off by some like small constant.
Okay.
So in my research, I have proved exact guarantees in different contexts spanning areas like standardized hash functions, one-way functions, zero-knowledge proofs, etc. Another challenge in the pipeline from theory to practice of cryptography stems from a matter of disparity in how we define efficiency in theory and practice. To quote Albert Einstein, in theory and practice are the same. In practice, they are not. In theory, efficient essentially means polynomial time, while in practice, we aim for concrete efficiency. That is, we are not only happy with polynomial time, we want the polynomial to be of small degree, have small coefficients, etc. This disparity comes from the fact that from a theoretical standpoint, we mainly care about what is feasible. On the other hand, in practice, we actually want constructions that we can deploy in the real world. To illustrate how far the gap between efficiency in theory and practice can be, let me take the example of zero-knowledge proofs. The first theoretical zero-knowledge proofs were introduced in the 1980s, but zero-knowledge proof systems being used in production became a thing only in the last decade. I've worked towards resolving this gap by giving new concretely efficient constructions of cryptographic objects that were considered to be only of theoretical interest before. I give constructions that are more efficient than all prior work, and moreover, they are optimal in terms of how efficient we can make a construction, assuming certain constraints. The specific area I've contributed to in this context is private information retrieval, something I'll talk about more later on in this talk. My work gives the current state-of-the-art practical single-server private information retrieval construction. Another challenge in the pipeline from theory to practice is that when we deploy constructions, we assume some underlying security model. And all our proofs are relative to the said security model.
So what do you mean by a single server private information retrieval?
There's only one server, and so of course, I guess your point is that it's with one server, like the server has to do linear computation for every query, so it's not really feasible. Is that your point?
In the sense that, I mean, usually, at least in one context of PIR that I know of, like you need at least two servers for it to be private. Otherwise, the server gets to see what your query is.
Here I'm mainly talking about computational private information retrieval. So yeah, information theoretically.
Are
you?
So you're interested in the computationally private analog of it.
Yeah, so I'm mainly so the thing with PIR is, of course, there are very good construction known for the multi-server setting, but then like if you think about practice, it's not a very realistic assumption to like what the multi-server setting requires is that the same database is copied at multiple servers who don't collude among each other. So like, for example, if you want to deploy private information retrieval on the internet, say you want to deploy it for like Google, for your Google search results, you don't want Google to know what you're searching for. But then it's not realistic that Google will have a copy of its database at like some other entity which it does not collude with. So that's why like there has been a recent like a surge of like works where people look at this context of single server private information retrieval, but then there needs to be, but then there are like known lower bounds that you cannot really do much in the single server setting information theoretically. So there's like different like things you need to consider. For example, like there has been a lot of recent work in like pre-processing private information retrieval, where there's initially a pre-processing phase where every client like does some pre-processing on the whole database, and this is like a one-time thing. And then based on the pre-processing, like the online time to retrieve is much faster.
Okay.
And a lot of these constructions are, so all of these constructions are based on like computational assumptions.
Okay.
Good. Okay. So another challenge in the pipeline from theory to practice is that when we deploy constructions, we assume some underlying security model. All our proofs are relative to the said security model, and often our security models oversimplify the picture of the real world. And our proofs and guarantees are only as good as the models that we assume, and the reality might be significantly different. For example, in an earlier slide, I showed you that one thing that influences the choice of security parameters is the running time of the best possible adversary that breaks a cryptographic system. This approach usually ignores all adversarial resources other than running time. And this is not ideal because often other resources like memory, randomness, etc. are also limited. And limiting them often has severe consequences on what an adversary can do. So I've contributed to a new line of work that considers memory as an adversarial resource in addition to running time for cryptographic proofs. This is important because real-world adversaries indeed have bounded amounts of memory. My work proves stronger guarantees against memory-bounded adversaries and therefore helps us set better security parameters, resulting in improved efficiency. So in a nutshell, I gave improved analysis of cryptography deployed in the real world. I also come up with efficient constructions that are efficient enough to be used in practice. Finally, I contribute towards a more general model that takes into account the memory of an adversary, something that had been traditionally ignored. I'll talk more about each of these contributions in more detail. Let me start with my work in giving improved analysis. The specific work I will cover gives exact security guarantees for standardized hashing. Hash functions are a fundamental cryptographic primitive. They are keyed functions that map variable length messages to fixed length digest. Here, the message X has variable length, K is the key, and Y is the output or the digest. They have numerous applications in practice. They are used in password hashing, in blockchains, and within the authentication mechanism of TLS, something that underlies a lot of the internet traffic. Because they are used so widely, NIST has standardized hash functions. These standardized hash functions are known as secure hash algorithms, or SHA. The first version of SHA, SHA-1, was actually broken in 2005 and therefore deprecated. SHA-2 is the next version, next SHA version. And so for this talk, it's not very important at all for you to understand these schematics I have on here. I mainly have them to point out that SHA-1 and SHA-2 are structurally very similar. And SHA-2 is widely used even today. However, the latest hashing standard is SHA-3, which was chosen after a long competition by NIST. Actually, at the time, there were a lot of very good candidates for SHA-3, but one of the reasons this particular construction was chosen is because it was structurally very different from SHA-1 and 2. The goal was to avoid any structural weaknesses SHA-1 had. The security property I will focus on is called collision resistance. It's one of the most basic properties of any hash function. And it requires that given a randomly sampled key, it must be hard for any efficient adversary to find two different inputs that hash to the same output. Almost all applications of hash functions require this property to hold. In most prior work, the exact security of collision resistance of SHA had been studied for collisions of arbitrary length. In particular, they gave an adversary showing that their guarantees are exact, but their adversary finds collisions that are huge, order of petabytes long. Such collisions are not of a lot of use to an adversary, even if it finds it. In practice, we predominantly care about an adversary only not being able to find much shorter collisions. For example, passwords are only a few bytes long. As such, it's natural to ask whether we can prove better guarantees for short collisions, because if we could set better parameters, which means improved efficiency. There was a wonderful work by Akshima, Cash, Drucker, and Wee in 2020 that actually considered this question for SHA-2. And they showed that indeed, finding short collisions is strictly harder than finding longer ones. And while this was a very good result that gave evidence that we could expect better guarantees for short collisions, there were many unanswered questions. The first was, if this is the case for SHA-3 as well. Moreover, it's well known that SHA-2 and SHA-3 have same security against arbitrary length collision finding. So it's prudent to ask if they are equally secure for short collisions as well. My work answered this question, and rather surprisingly, we showed that SHA-3, which was supposed to be an improvement on SHA-2, is less secure than SHA-2 for very short collisions. And in fact, the difference in structure of SHA-3 compared to SHA-2 is what leads to this reduced security. I'll talk about this result in more detail. To do so, I need to first introduce to you the structure of SHA-3, at least a simplified version. It is based on what is known as the sponge construction. The fundamental primitive in this construction is a permutation pi. In order to hash a message M, it is broken up into chunks of R bits. Here, the chunks M1 through MB are known as message blocks. The hash of M with respect to the hash key K is defined as follows, is computed as follows. An initial state consisting of R zeros concatenated with the hash key is defined. And then the first message block is XORed with the first R bits of the state, and the permutation evaluated on the result to get the next state. This is done till all the message blocks are consumed. This phase of hashing is known as the absorption phase of the sponge. Next, the permutation pi is applied to the final state at the end of the absorption phase, and the first R bits of the output forms the hash output. And this last application of the permutation is referred to as squeezing. The absorption and squeezing actions are what give sponge its name. The specific thing that I will talk about here is the resistance of SHA-3 to one block collisions, that is collision resistance for extremely short messages. Essentially, for one block collisions, an adversary given a random key K needs to find two messages M and M prime, such that the evaluation of pi on M K and M prime K produces the first, produces identical first R bits of output. Here, so was there a question?
No.
Here, using index 1, I denote the first R bits of the state, and using index 2, I denote the last C bits of the state. The shaded rectangles denote that the value in those paths are identical. So in order to show that SHA-3 is indeed less secure than SHA-2 for one block collisions, what do we really need to do? We need to first understand what is the best we can do for SHA-2, that is find an optimal adversary that finds one block collisions in SHA-2. A prior work by Dodis, Guo, and Katz does that already. So all we need to do is give an adversary for SHA-3 that does better than the optimal adversary for SHA-2. We do this by giving an explicit time-space trade-off adversary that does better than the optimal time-space trade-off adversary against SHA-2. But first, let me informally define what a time-space trade-off adversary in this context is.
So, if I'm allowed, polynomial time, then what you're saying is an easy problem, right? I have just to invert the pi, and then there's nothing more to it, or am I misunderstanding? So, if I'm allowed polynomial time and polynomial space, then then this problem is just inverting pi, right? Because pi is mean.
No, like the thing is you're truncating the permutation, right? Like so the for one block collisions, the output is just this. So you're given this key k, and then like you're not given the entire output. You're just given like the output of the hash is like the first R bits.
Okay.
And yeah. In fact, the reason you need to truncate is because otherwise, like if the whole state was output, there would be no collisions at all because it's a permutation. So the reason there are collisions is because there's it's truncated. Okay, so let me informally define what a time-space trade-off adversary in this context is. So a time-space trade-off adversary A, it consists of two stages, A1 and A2. The first stage, A1, is unbounded and has complete access to the permutation pi, which is modeled as a random permutation. A1 computes S bits of advice or preprocessing, which is input to the online phase, A2, along with the random key K. And the online phase can make at most T queries to the permutation and its inverse. A2 wins if it can output a pair of distinct one-block messages that hash to the same output. This model captures real-world adversaries because the underlying permutation for sponge is publicly known, and a very powerful adversary, for example, the NSA or some malicious government, might be able to do a lot of preprocessing on it. This also captures non-uniformity. I'll give you a high-level overview of the time-space adversary that we come up with that finds one-block collisions in SHA-3. The main idea underlying our adversary is to turn the collision finding problem into a random function inversion problem. But first, what is random function inversion? So in the random function inversion problem, an adversary is given black box access to a random function f that maps c bits to c bits. The problem requires that given a random b, the adversary has to come up with an a such that f of a equals b. Again, one can consider this problem in the context of time-space trade-off adversaries, where the preprocessing phase gets unbounded access to f and computes some advice, and the online phase gets the advice along with the input b. A seminal work by Martin Hellman formally studied function inversion in this context and gave a non-trivial time-space trade-off adversary for random function inversion. What we do here is, given Hellman's adversary, call it B, we construct an adversary A that solves the collision problem that we are interested in. A will run B as a subroutine. This is essentially a cryptographic reduction. I'll show you a sketch of this reduction now. This is the main step of my result. So to begin with, I'll make adversary A's life a little more hard. So instead of solving the collision problem, I'll make A solve this. We want A to find M and M prime such that the first R bits of the evaluation of the permutation on MK and M prime K are both all zeros. Of course, if A succeeds, it has solved the collision problem as well. The choice of making A solve a harder problem will be clearer soon. So in order for A to solve this harder problem, we will take an alternate view of what A needs to do. Namely, we'll define a function f that has c bits inputs and outputs. This function f on input x computes the pi inverse of r zeros concatenated before x and outputs the last c bits. I'd like to note at this point that the function f is independent of k. We switched to solving this harder problem because we want f to have this property, and this is the property that would help us use Hellman's time-space trade-off adversary. Let's see how. So the adversary A given K, computes two distinct inverses, X and X prime of K under F by running adversary B twice. A can do this because F does not depend on K, and therefore its preprocessing phase can run the preprocessing phase of B, and then its online phase can run the online phase of B with the key K that A itself gets in the online phase. A then computes M as the first R bits of the inverse of pi on R zeros concatenated before X, and similarly computes M prime and outputs them. So why does this work? Observe that if X was indeed an inverse of K under F, the last C bits of the output of pi inverse on R zeros concatenated with X is K. Additionally, by definition, we know that the first R bits of the output of pi on R zeros concatenated with X is M. So this means that when we evaluate the permutation pi on M concatenated with K, the first R bits are all zeros, which is what we want. And we can argue the same thing for M prime. So we have succeeded in reducing the collision finding problem to a function inversion problem. There are, of course, a lot of fine-grained details that need to be handled here for this to work out. I'll not go into those details in this talk. I'm happy to tell you more about it offline if you're interested. So with that, I'll quickly summarize the key takeaways of my contributions to this line of work before moving on. The main takeaway is that SHA-3 is less secure than SHA-2 for very short collisions, even though the former was supposed to be an improvement. The reduction that I gave does not generalize beyond one block messages, but there's been a follow-up work published at TCC last year that shows even for two block collisions, SHA-3 is less secure than SHA-2, but uses very different techniques. I've also several other generalized results about short collisions in both SHA-2 and SHA-3, but due to interests of time, I'll not be talking about them here. Another area of cryptography where I've given improved analysis is zero-knowledge proofs that are deployed in cryptocurrencies like Monero. And to get these results, I've used tools from areas ranging from combinatorics, information theory, algebra, etc. Are there any questions? Okay.
No.
So, okay, with that, I'll move towards my contributions in giving concretely efficient constructions that make purely theoretical constructions closer towards practice. I'll specifically tell you about my new state-of-the-art construction in private information retrieval. So information retrieval is a problem that crops up in many different contexts all the time. For example, suppose you want to book an Air India flight from Mumbai to New York. You will first Google Air India's webpage, and Google will retrieve a set of search results. Then when you go on the Air India website, you enter your source and destination, and the website would retrieve the flights, prices, etc. However, what this means is that Google knows your entire browsing history, and the Air India server learns of your potential travel plans even before you have bought tickets. And this is not ideal, especially in the light of massive data leaks exposing our browsing history and other private information. Even something like genetic data that cannot be changed has been leaked of late. In such a scenario, plain information retrieval from servers is not a very satisfactory solution. To prevent such scenarios where the server learns what the user looks up in a database, Chor, Goldreich, Kushilevitz, and Sudan introduced the notion of private information retrieval, which is abbreviated as PIR. This is a cryptographic mechanism to retrieve the ith bit of the database that is stored on some server without the server learning what I is. One could consider notions of PIR where there is more than one server, each of which hold a copy of the database and are non-colluding. However, in this talk, the particular setting I'll be focusing on is single server PIR. The database here is public, but the query of the user is private. So PIR, if scalable and practical, is almost like a silver bullet that allows amazing applications like private DNS, private browsing, private search engine, etc. However, as with all nice things in life, there's always a caveat. Result by Bimail, Ishai, and Malkin shows that in the classical single server PIR setting, for every query, the server needs to do computation that is at least linear in the size of the whole database. And this is not great because even for gigabyte-sized databases, this would make the time needed to respond to one query in the order of several minutes, which is not very practical for a retrieval problem. Although in a more positive development, there's been a recent paradigm shift following the work of Corrigan, Gibbs, and Kogan, which introduced the model of client-side preprocessing PIR. So in this model, there are two phases. In the preprocessing or offline phase, the client communicates with the server and stores some hints. In the online phase, the client makes queries that depend on these hints. It already has from the preprocessing and receives the.
Ashrujit, I have a question. Could you just define single server PIR and what kind of guarantees you want from it? I think I missed that part.
Like you mean efficiency guarantees?
No, but what, I mean, privacy guarantees in particular.
So privacy guarantees, like informally, it means that say you want to retrieve the ith bit of the database and the server doesn't learn any information about I. Like the server's view, irrespective of what you query for any like ij, so the server's view has to be identically distributed.
In the computational sense, because it's...
Yeah, in the computational sense, yeah.
And we are thinking of this as a single round thing, or we should think of this.
So typically for PIR, we like the constructions that are there are all single round thing, but you can consider like a more interactive definition.
Okay.
But yes, typically like all constructions are single round.
Okay, thanks.
Okay. So in this model, there are two phases. There's an initial offline or pre-processing phase where the client communicates with the server and stores some hints. And then there's an online phase where the client makes queries. The queries depend on these hints, and it receives answers from the server. And the hope is that the time needed to answer these online queries is significantly faster than a linear and the server needs to do much less work than a linear in the size of the database. And it turns out that this model brings PIR much closer to practice because this expensive pre-processing phase is the one-time thing, and the online queries require much less server computation and communication. Meaning that even for gigabyte-sized databases, the queries can be answered in like order of tens of milliseconds. And constructions in this model are more practical than earlier PIR construction. Let me first set the stage by talking about the prior state-of-the-art work. So the most efficient theoretical construction for client-side preprocessing PIR was based on public key assumptions. By public key assumptions, I mean assumptions that are known to imply public key cryptography. For example, lattice-based assumptions like learning with others, etc. The two efficiency parameters that we mainly consider are the server computation and online communication, because these are the two parameters that essentially determine the response time for online queries. And this is what we want to minimize as far as possible. For client-side preprocessing PIR, the best constructions from public assumptions have server computation O square root of n and online communication O polylog of n. And just as a comparison, there was a recent theoretical breakthrough result that considered server-side preprocessing, where the server does the preprocessing of the database instead of the client, and it actually achieves both server computation and online communication O polylog of n. However, the amount of storage the server requires for this which asymptotically is O n power 1 plus epsilon. But this O hides really large constants. And a paper recently tried to estimate the storage required. They could not implement it because the storage was prohibitively large. And from some calculations they did, they showed that a 10 megabyte database would require roughly 10 power 78 bits of storage on the server, which is not feasible by any means. Even with these client-side pre-processing PI constructions from public key cryptography, because public key cryptography is very expensive, these schemes don't really have concrete efficiency and are not very suitable to be used at scale.
How large are the hints that we are talking about? In the sense that how much is the pre-processing step at all?
So typically the pre-processing step would have to be linear in the size of the database. And then the goal is that so generally, like in typical construction, what happens is like the client scans the whole database in the pre-processing phase and like stores some hints based on that linear scan. And then in the online phase, the hope is that it needs like the server and the client need to do computation that is sublinear.
I mean, like, what is preventing this client from just storing the database at the client's end?
That requires huge amount of client storage. So I would also want client storage to be sublinear, because that also like is like, say you have a terabyte size data, like terabytes of size database, and like you have a very like low end client. Say you are using a mobile phone.
Okay.
So yeah, so we typically want like client storage to be sublinear, like in the size of database, like at least like it's better if we can make it like polylog or something, but at least sublinear. We want like sublinear server computation, sublinear client computation, and sublinear communication, like at the very least.
Okay.
So instead, so we want constructions from mini-crypt assumptions. So these are assumptions that are not known to imply public key cryptography. And one of the reasons we prefer these constructions is because public key operations are very expensive and we want to avoid them. Moreover, mini-crypt only requires pseudo-random functions, and AES can be used to implement pseudo-random functions. And most modern CPUs support the AES instruction set, meaning that AES operations are extremely fast. Therefore, constructions based on mini-crypt assumptions are concretely efficient. The state-of-the-art result using mini-crypt assumptions had both server computation and online communication O square root of n. And as an aside, a follow-up work has shown that improving the server computation is not possible using mini-crypt assumptions. In my work, I give a new construction that improves the online communication to O n power quarter instead, keeping the server computation the same. This is currently like the best as practical single server PIR construction, and one of my co-authors implemented it, and we found that for a 64 gigabyte database, the online communication of the scheme is almost a 50-time improvement on the prior state of the art. And to give you some concrete values, the response time for queries for like a similar size database is in the order of like tens of milliseconds, which is, while not super practical, is more practical than prior work.
And if the privacy breaks, what if the privacy? So what the security? So if the privacy of this scheme breaks, then AES has a break of what kind? Like it can be solved in like is that?
So typically people assume that like 4 rounds of AES is a pseudo is a PRF. So like.
So that it is a PR, it's a pseudo generated with some distance from uniform, some small distance to uniform, distance to uniform.
Yeah, like it's a heuristic, like there's no real like formal proof, but the thing is like it's kind of like one of those assumptions that you need to use if you want to build anything practical, because like all like theoretically secure constructions of pseudo-random functions are like way more expensive.
But
So like
even in this case, so the heuristic thing would be that if the privacy does not hold, that AES output does not look pseudo-random in some
yeah, like essentially what is like the proof would show that like if you can compromise the privacy of the PIR scheme, you can essentially like break the like you can win the PRF game. So that like it's a reduction to the PRF security. So yeah, essentially you can distinguish the output of like AES from like a random uniform random.
And in this particular example that you have, how much pre-processing is used? Is that also order square root n or?
No. So the pre-processing has to be a linear scan. So it's like order n. The pre-processing is order n, but the point is you just need to do it once, and then you're done.
We have still got, so what does the query to the server look like in the pre-processing step? Or do they actually communicate for order n? I mean, is the entire database transferred, but it's just that the client doesn't store the entire database?
Yeah, so typically, so all these three constructions I have on here, what they do is basically the client streams the whole database. Like it reads the database as a stream. It does not need to store the whole database at once. Like it can compute the hints on a streaming fashion. Like square root n memory suffices. It does not need memory more. Like at one point, it does not need to hold more than that of the database during pre-processing. And then like it stores some hints, which would be like roughly, which would again take storage like square root order of O of square root n. And then like online communication in our case is we get n per quarter, but then yeah, the client computation and the server computation would be like square root of n.
Okay.
Also, like this is a very this client-side pre-processing PIR is a very new like line of work, and all these like works are very like I think there's a lot of like design space that needs to be explored, and I'll talk about my future research agenda at the end. And I think there are lots of very nice questions that need to be answered in this area. Okay. So I'll very briefly talk about the key technical ingredient that underlies this result. The one-line summary is that we relax an underlying primitive that a prior work uses. In more detail, the prior work used a primitive called a privately programmable pseudorandom set, and we relax it to a weaker primitive which only supports list decoding. I'll summarize what these objects are. So a privately programmable pseudorandom set is a cryptographic primitive defined by 4 functions: gen, set, program, and decode. Gen returns a secret key sk. Set takes that secret key as input and produces a set s. Program takes as input a set s, an index l, and a value y. And it produces a secret key sk prime. And decode takes as input a program key sk prime and returns a set s prime. The correctness requirement is that the set s prime returned by decode is the set s with the element at index l replaced by y. Very informally, the privacy requirement is that the set s looks somewhat random. Our new primitive is almost exactly the same, except that instead of decode, we have a list decode function, which on input a program key outputs a list of sets S1 through Sm, and the correctness requirement is that the correct decoding of Sk prime is among the outputs of the list decoding procedure. And what we show is that this weekend primitive is sufficient for client-side pre-processing PIR. And our efficiency improvement comes from the fact that we can implement this using much lower online communication. With that, I'll summarize the key takeaways from this line of work before moving on to the last part of this talk. So there's been a recent paradigm shift that's made practical PIR a possibility in the future. And My recent work is the current state of the art for practical PIR constructions. And my improvement comes, it is completely down to a relaxation of the definition of an underlying theoretical primitive. That question. So finally, I'll talk about my work in giving general models that paint a more complete picture of the real world. Specifically, I'll describe my work that's augmented security proofs to consider memory of an adversary as a resource. So classical concrete security theorems in cryptography show that against all adversaries up to a certain amount of running time, a construction is secure. In other words, they consider running time as the sole adversarial resource. And of course, this makes sense because there are well-known bottlenecks on how fast computations can be done. And also considering running time makes, only running time makes proofs relatively simpler. However, running time is not the only bounded resource. Another bounded resource is memory. For example, the most powerful supercomputer has less than 10 petabytes of main memory, which translates to roughly 2 power 57 bits. Now, even if we pool all available computational resources, it is reasonable to assume a memory upper bound of, say, like 2 power 72 bits, like just as an example. But of course, it's prudent to ask, does it even matter? Like, does bounded memory affect adversaries? The answer is best illustrated by an example. Consider the discrete logarithm problem in prime fields. It's one of the favorite problems for cryptographers. The graph here shows for which time and memory values an adversary is known to solve this problem. So observe that when a lot of memory, like 2 power 78 bits, becomes available, the fastest known adversary is much faster than one that does not have that much memory. In particular, if we assume a memory upper bound of, like, say, 2 power 72 bits, the fastest known adversary takes 2 power 2048 time. Therefore, such a scenario allows us to set security parameters way more aggressively, leading to more efficient constructions. So what we saw in the previous slide is that in some cases, there's a kind of
Can you go back to the previous this one? So with the graph which you're drawn is a statement of complete efficiency or what? That is stating that if 2 power s is larger 2 power s is larger than this, then there's an algorithm, and if 2 power s is smaller than this, there is no algorithm. Is that?
No, so it essentially says, like, so I'm like, so for this, like, I've plotted, like, say, like that. I want to, so these are like concrete numbers. So I'm plotting, like, okay, I want an adversary to achieve like advantage, like 10 power, say 10 power minus, like 10, like 2 power minus 10. Like, say I set that threshold, like, say an adversary breaks like the discrete logarithm problem with probability like 2 power minus 10. So for that, I would need like 2 power 78 memory and 2 power 156 running time. So I've set like a probability threshold here.
No,
like below that.
Okay, go ahead.
So below that, I say that, okay, so here that's what I mean by unsolvable, as in, like, it's not really significant. And above that, I mean, like, okay, it's solvable. So that's how I like plot this graph.
My question more is the unsolvable. You're stating that the memory is less than a particular concrete number, then it requires so much more time. This is on an assumption. What is the concrete efficiency assumption you need for?
So this is based on, like, this. So this graph is based on best known attacks. So I can't prove. There's no proof that discrete logarithm is unsolvable in this regime. There's no proof of that. But, like, if you take like all known attacks, and this is like a well-studied problem. So, like, it's you can, like, people typically, like, when you deploy things, you typically look at what's the best known attack. And so, like,
okay, so my interpretation is when you say pi needs running time under current known attacks.
Yeah.
Okay.
Yeah. So this is like, of course, ideally we would want to prove like pi needs running time, but so far we don't really have any proof for like any computationally hard problem that where we can show that there's like a trade-off, like there's a known trade-off. Like all these trade-offs are based on like the best known attacks.
No, one could expect to prove such things based on assumptions on compute efficiency.
Yeah. But like, yeah, without assumptions, I mean, like.
Okay.
Just building on that, like, are there any attacks known for the discrete log problem that try to optimize on space at all?
So for example, like this 2-part 2048, this attack, like this is essentially memoryless. Like it requires like some small constant amount of space. Like but other than that, like initially the first work that came up with this attack used memory, but then there were follow-up works which showed that you don't really need memory at all. But for this regime, at least I don't know of works which do that.
Like if the memory is really high, then maybe there are better algorithms. That's what the graph section says, right?
Yeah.
So there may be attacks that use really large.
No, because the standard, whatever, if you use any of the sealing techniques and so on, you're going to make a fairly large. Yeah.
That's 7 to the power 8, right?
No, it's 10 to the power 70. Like,
No, 7 plus 8 times 9.
Oh, that's 8.
Okay.
8 times 9. Very easy.
70 to the.
Oh, that's 70. No, that's 78 or 70. 78. The 7 to the 8 is like enormous.
no, that number is 70.
70.
Yeah, we can go ahead.
So I'm curious, like, did it just happen that 78 is half of 156? Like, why is that?
Yeah, like it's like so this is the number. I don't know if you've heard of it. So it's called the number field sieve algorithm. So it's essentially some variant of NFS which solves this. And yeah, it's like the running time is like squared of memory.
I see. Okay.
So, okay, so what we saw in the previous slide is that in some cases, according to best known attacks, there's a trade-off between time and memory required by an adversary to break cryptography. So it's natural to ask, are these trade-offs applicable to any cryptographic system? Turns out they're not always applicable. Sometimes the fastest adversaries use little to no memory at all. So it's a nuanced scenario, and that needs us to revisit all security proofs to account for the memory of an adversary. And my research has contributed towards that. I've shown time memory trade-offs in some cases, while showing that trade-offs are not possible for some particular proofs in other cases. This is a very new area in cryptography, and there are all these works showing that showing trade-offs or showing that they are not possible for particular proofs. And I've contributed to both lines of work. In particular, I gave the first result that takes memory into account for a concrete scheme that is used in practice. I've also studied time memory trade-offs for TLS. And more recently, I developed a new toolbox that helps us show these time memory trade-off results. I'll very briefly describe at a high level the main idea underlying this toolbox. The starting point for this is to consider the fact that security proofs proceed via reductions. So, for example, when we prove that the hardness of pi implies a scheme sigma is secure, what we really prove is that given an adversary A that breaks sigma, we can build a new adversary R which runs A to solve pi. Often there are known time memory trade-offs for pi, and we want to show time memory trade-offs for security of sigma. For this, we need a reduction R that preserves this trade-off. What I mean by this is, so what needs to happen is the memory of R when it runs A should be very close to the memory of A. Taking a step back, so the main task R needs to accomplish here is that it needs to simulate the challenger for the security game of sigma in a way that it is indistinguishable to A from its interaction with the real challenger. And this simulation often requires R to store some state. And for R to preserve time memory trade-offs, this state has to be small. The starting point of my toolbox is this following key observation. So for some reductions, if R answers some query with some value little a, it needs to hold some state sigma a that will be used only if the adversary sends back little a at some point in the future. So in order to make such reduction use limited memory, we need to figure out a way to avoid storing the state sigma a. And we call our main idea hiding in plain sight. We figure out a way to hide this sigma a within A itself and then recover it later. Of course, this is not always possible, but when A has enough redundancy, this can be done. And it turns out in many cryptographic proofs, this is indeed the case. Due to interests of time, I'll not go into concrete examples of this, but I'm happy to tell you more about this offline. So the key takeaway from this line of work is that memory matters in cryptography. It should not be ignored. Only recently, there's been an effort to look at cryptographic reductions from a memory point of view. And this area uses technical tools from various areas like communication complexity to linear algebra, etc. So I'll conclude this talk with a broad outline of my future research plans. So an ongoing focus of my research is to demystify the landscape of preprocessing PIR. So with recent progress, we seem increasingly close to making PIR practical. And one of the fundamental questions I want to understand is what assumptions are necessary for preprocessing PIR at different regimes of efficiency. I aim to also understand how far we can go to make PIR efficient. In some ongoing work, we have some more progress in this direction. Further, lower bound techniques for proving limitations of PIR are very few and far between, and the known results are extremely weak. I want to explore coming up with newer and richer techniques that help us prove meaningful PIR lower bounds. Another direction I want to look at in my future research is to build a more complete picture of various resources required by an adversary to break security, for example, parallelism, randomness, etc. Moreover, I hope to develop better abstractions and frameworks for analyzing trade-offs between various resources. Having worked quite a bit on time memory trade-offs, I've found that existing tools and techniques are very ad hoc. I want to develop something more generic so that we don't need to do a case-by-case analysis for different cryptographic constructions. In recent work, we have made some very initial progress towards this. A long-term goal for me is to develop more techniques to analyze exact security of complex cryptographic systems. A lot of cryptographic constructions have connections to different objects that are well studied in theoretical computer science. I hope to find new connections that lead us to improved constructions for complex cryptographic objects. Another goal for me is to develop a theory that studies the exact security of cryptographic systems against quantum adversaries. So with the looming threat of quantum computers, it's essential that we understand how secure our cryptographic systems are against quantum adversaries. And while there's been a lot of recent progress on feasibility security results in this context, very little is known about concrete security of cryptographic systems against such adversaries. And this requires a lot of new theory to be developed. Finally, in the last couple of years, there has been a tremendous increase in text generation using large language models. And one challenging issue in this context has been detecting what text is produced by LLMs. And there's been attempts to build solutions for watermarking text generated by LLMs, but most of the ones that are used produce a large number of false positives. Some very recent work over the last year has looked into undetectable watermarking for LLM generated text using cryptography. And while they have proposed very nice theoretical solutions, there are inherent limitations for it to be practical. I want to explore this direction of research to see whether watermarking in LLMs using cryptography could be made efficient or if it's not possible. Thank you for listening to my talk. I'm happy to take any questions that you might have.
Can you summarize the model for watermarking? Or is there a standard model? What is happening there?
So there's only been like one work, so it's not. I wouldn't say it's like a standard model. Like like what in that work, what they do is they consider like essentially they look at like watermarks as like digital signatures, and one of the issues with that is like you kind of need a signing key that needs to be kept secret, and that's not a very good thing, because like who stores that secret, and how do you make sure that it doesn't get leaked so that like people can forge signatures. So the way that it is studied, like at least in the one work that studied it, it was almost like it's in a model very similar to like digital signatures.
So my worry is that I can ask ChatGPT to give me a page of text and I can take every other word. So this would not, in all the models I know, I think this would spoil the signature or watermark, whatever. I can ask it to generate something where every other word is unimportant, and then I ignore it.
Yeah, like so you're saying that you're some kind of like malleating that text generated by LLM, right?
Yeah.
Yeah, I don't think that paper like considered this problem. Like it just looked at like watermarking, and I think one of its other focuses was like the text should be like indistinguishable from like non-watermarked text. So yeah, I did not consider like any kind of like malleating attacks or anything.
More questions? Yes, thank you, Marianne. So thank you. I think we are meeting next. It is 5:06. So you want to take 10 minutes before we start?
Yeah. So yeah, that's yeah. I can come back after 10 minutes if that's fine.
So we'll use the same link.
Okay. So see you in 10 minutes.
Okay. Bye.
Person in the position is no longer.